This section explains the FlashAttention model and code implementation. Let's first look at the FlashAttention model overview. FlashAttention is a memory-optimized version of the standard attention mechanism used in transformers. By utilizing more efficient memory management techniques and simplifying some components of the traditional attention process, FlashAttention can handle longer sequences with lower memory overhead. Scaled dot product attention. The core mechanism behind FlashAttention, like traditional attention in transformers, is the scaled dot product attention mechanism. The attention scores are computed by comparing the query vectors to the key vectors and then using those scores to weight the value vectors. The formula for standard scaled dot product attention is as follows. Q is the matrix of queries, K is the matrix of keys, V is the matrix of values, dk is the scaling factor. It ensures that the dot product doesn't grow too large as the dimensionality increases. The attention weights are computed by taking the dot product of the query and key matrices, scaling them by dk, and then passing them through a softmax function. This ensures that the weights sum to 1 and represent a probability distribution. These weights are then used to compute a weighted sum of the value vectors, which is the output of the attention mechanism. FlashAttention optimization. Key concepts of FlashAttention. 1. Multi-head attention. FlashAttention, like other attention mechanisms in transformers, employs multi-head attention, where the attention is computed multiple times with different weight matrices, one for each head. This allows the model to attend to different parts of the sequence using different attention perspectives. The idea is to split the input dimension into multiple heads, each with a lower dimensionality, and then aggregate their results. This is done by creating multiple queries, keys, and values, and performing the attention mechanism separately for each head. Queries, keys, and values are projected through linear layers and then reshaped to split into num heads attention heads. The attention mechanism is applied independently to each head, and the results are concatenated and passed through an output projection. 2. Memory efficiency and tiling. The standard attention mechanism, while computationally efficient, can consume a lot of memory, especially for long sequences. FlashAttention introduces a technique called tiling to improve memory efficiency. In the tiled FlashAttention, the sequence is divided into smaller chunks, or blocks, of the sequence, and the attention calculation is performed on each block separately. This allows the memory footprint of the attention matrix to be reduced, as only a small part of the sequence is processed at a time. Let's break down how this works with the tiling method. 1. Block division. The sequence is split into smaller blocks. Let's say the sequence has length L, and we split it into blocks of size B. Each block will process B multiply B attention weights at a time, where B less than L. 2. Attention calculation per block. For each block, we compute the attention scores only for the positions within that block. This reduces the memory cost. The attention scores for the block are computed as follows. The mask is applied if there are any padding tokens in the sequence. 3. Softmax and dropout. For each block, we apply softmax to normalize the attention scores and dropout for regularization. 4. Block output. The output for each block is calculated by taking the weighted sum of the value vectors based on the attention scores for that block. 5. Final output. After processing all blocks, the results are concatenated and projected back to the original dimension. Now we implement the FlashAttention code. FlashAttention class. FlashAttentionWithTiling class. Testing the FlashAttention model.